So we will extend the idea to 2D, and then we will actually generalize it to beyond 3D. So in 1D, we said the equations are mq double dot plus cq dot plus kq equals f in 2 dimensions. I'll just write a matrix equation. It's easier to deal with it. M11, M12, M21, M22, Q1 double dot, Q2 double dot, plus C11, C12, C21, C22, Q1 dot, Q2 dot, K11, K12, K21, K22, Q1, Q2 equals, my God, I'm running out of space. Okay, so this will be F1, F2. Okay, so what we said was, how about defining F as minus KPQ minus KDQ dot, right? So what would this look like in 2 dimensions? Well, it will be F1, F2 equals minus KP11, KP12, KP21, KP22, Q1, Q2 minus KD11, KD21, KD12, KD22, Q1 dot, Q2 dot. Okay, so what we have here is 4 parameters and another 4 parameters. And because it's a feedback control system, you have to make a choice on what you'll make those parameters. So we have 8 parameters. But the question is, when you're solving for parameters, you need equations or conditions under which those things are true, right? So to make it critically damped, so to have a critically damped system, we'll have two psis, psi1, psi2. There will be 2 equations. Okay? So 8 parameters, 2 equations, and that's where the problem is. If you have 2 equations to solve for 8 parameters, then 2 can be determined from those two equations, but there are 6 free parameters. So free parameters are 8 minus 2 is 6. This is just too many. Right? For the first example, we just had one free parameter. In fact, it was very easy to check what that free parameter does. As we increase that parameter, the system damped out early and early. Right? It reached 0 fast. This is going to be a nightmare to tune or choose 6 numbers. It can be done. And then if you go to 3 dimensions, 4 dimensions, the number of free parameters keep increasing. So this is not a very good solution. We just don't want to keep tuning parameters. So this is where we get to a method called feedback linearization. Sometimes it's also known as control partitioning. So you'll see that method will actually help us to dramatically reduce the number of parameters. In fact, for 2 degrees of freedom system, we'll only have 2 parameters to tune and 2 equations, sorry, 4 parameters and 2 equations. So two need to be chosen by the user. And then for n dimensions, the same thing. You'll have n parameters which you need to choose, and then the other n are given by the condition. It's really easy to tune that. Okay, so let's look at what feedback linearization does. Okay, it's a very powerful idea. So next is feedback linearization, or also known as control partitioning. And to deal with this, what we'll do is, why just look at two-dimensional system? Let's look at the n-dimensional system. We just make it work for n dimensions. So the dynamics of a manipulator are given by this equation. So that's the dynamics. Now, just write this. Yeah, and I'm free to choose whatever I want for the control. So the feedback control, which will make this possible, which will make it really our life very easy, is to choose tau such that it is, and the form is very important. Okay, so pay attention. M minus Kp Q minus Kd Q dot plus C Q Q dot times Q dot plus G of Q. Okay, so this is the tau, and then it is a feedback form because you're feeding back Q. In fact, you also need Q dot. So what we assume here is Q dot, Q is positions, Q dot is velocities, are measured by onboard sensors. Okay. So you just have the measurements. If you have the measurements, you have this form, then something magical happens. Let's see what happens by substituting the second equation in the first one. So let's call this 1, let's call this 2, and let's substitute 2 in 1. So here we go. So I just substituted the value for torque. This is tau. Okay, so what we observe is that this C cancels with this C. This G cancels with this G. Okay, next what I'm going to do is I'm going to move this this term to the left. So I can write M in brackets Q double dot plus KP U. Okay, so we have an equation which says M times that whole thing equal to 0. Now the mass matrix is never singular, it is never 0. Since unless you have no mass, which is not possible. So since M is not equal to 0, when I say M is a matrix, so really we're talking about determinants. Determinant of M is not 0. So then we can say that Q double dot plus KPQ minus KDQ dot equals 0. Okay, so for a moment, let's think what this equation really means. This is not a scalar equation. It's actually a matrix equation. Okay, this is an n-dimensional equation. I should have put it here. Notation is it belongs to Rn. This just means that it's of n dimensions. So this is a n cross 1 n cross 1, n cross 1, and this mass matrix is really n cross n, is n cross 1. Okay, so it's n dimensional. I'm just going to expand this out. So I'll rewrite this equation in a matrix form. So here it is. Q1 double dot, Q2 double dot, Q3 double dot, so on till Qn double dot. Okay, so here's what the Kp looks like. It's kind of interesting. Kp is actually Kp1, let's just put 1, and all zeros, Kp2, and then all zeros, Kp3, all zeros, and so on, Kpn, and then this will be multiplied by Q1, Q2, Q3, so on till Qn. And then there's a third term, which I'll copy from here. So the third term would be KD1, KD2, KD3, KDN, will be Q1 dot, Q2 dot, so on till Qn dot equals 0. Okay, so very, very interestingly, what you have achieved is this equation. And if you actually write down, there's actually n equations, right? You can write n equations down. So these are n decoupled equations. So they will look like this: Q1 double dot plus KP1Q plus KD1 Q dot equals 0, Q2 double dot plus KP2Q plus KD2 Q dot equals 0, and just keeps going on till Qn double dot plus KPNQ plus KDNQ dot equals 0. So really what these equations, you have just have this equation. I'm just going to, let me just keep it as it is, KPI Q. Okay, I will go from 1 all the way to n. So this is exactly the similar to, well, this is not exact, but it's very similar to the one-dimensional equation we talked about. The one-dimensional equation we talked about with the control, of course, is this. Okay, and then for this equation, we said KD is minus C plus 2 square root K plus KP times M, right? This is something we already got. Now what we have here is this equation, Qi double dot plus, I'm just going to switch the equation had Qi double plus KPQ plus KDQ dot. I'm just going to shift this QD, I'll take KD first and then KP. Now you can compare this equation with this equation, call it 1 star. They are very similar. In fact, if you put m equals 1 in first equation, c plus, so c equals 0 and k equals 0 in 1, then you should actually get 1 star. Okay? Which means if you want to find KDI, it's minus c plus 2 square root k plus kpi m. That would simply be KDI equals minus c is 0, plus 2 square root k is 0, kpi m. Okay, which means that your KDI is simply 2 square root m times kpi. Let me just put it as, well, m is my bad. That's it. So this is, that's the equation. Very, very simple. KD is 2 square root kp. And you can do this for I equals 1, 2, so on till n. And then your all the degrees of freedom will be critically damped. I just made up some random system with some mass matrix, some Coriolis term C, some K, and then here Kp is, as I said, it's a free parameter. You can choose whatever you want. Kd is 2 square root Kp, it's the same expression I wrote. And note that this is diagonal. Kp is diagonal, 100 times the identity, and 2 square root, it'll also be diagonal. So here what we're trying to do is, instead of trying to regulate it to 0, 0, we're trying to regulate it to 0.5 for Q1 and 0.1 for Q2. And to make it my life hard, I said that I don't really know what mass is and the C is and K is. I introduced some perturbation. So the mass parameters are off. Okay, so then control partitioning, basically same formula I wrote down earlier. Well, this one actually uses the identified form. This one is, well, let's just use the first one. Here I'm assuming that I know m hat, I know c hat, and so on. M hat, c hat were this thing which was the actual mass plus some random things I added. Okay, so then I just do feedback linearization, and it's essentially ODE int. If you do this, you will see that it'll actually go from, start from 0, 0 for Q1 and Q2, and it will actually go to 0.5 and 0.1 is what I set it to go. So first plot Q1, I wanted it to go from 0 to 0.5. The red is the set point. It goes to 0.5 rather quickly. And then for Q2, I need to go to 0.1, it goes there rather quickly. Now, if I say that I do not know, remember that when I have this M, C, and K, but M hat is M plus whatever. So usually what happens is when you look up a spec sheet of, let's say, a manipulator, it'll give you the mass C and K that's in the spec sheet. But the actual mass and C and K would be different because maybe there was machining defect or manufacturing defect, or maybe your C hat, for example, that's damping. So maybe there was damping introduced because your gears, you lubricated them again. So that could change. So what happens if that changes? So here what we'll do is we'll not use the correct model. We have the incorrect model. We think it's MC from the spec sheet, but it's actually M hat. So let's run this and see if that works. And I think that will give you some errors. Well, actually, it does pretty well. It's actually spot on. Now, if you keep increasing that, then I think it'll be a problem. So if you go here, and then this is the very small values, but let me make it 5 times this, and I don't expect it to work as well as it did. Well, actually, it does pretty well. Okay. So when it's too much off, you might have to go back and redo a system identification on the hardware so that it works right. Okay, so that's that. That basically is a made-up example. I'm going to show you an actual example involving like a system, a physical system. So let me just put it there in the notes. So you want to look at so example I showed you will be in this file. It's called C Python file. It's in this folder control. Yeah, so when I give you the files on Blackboard, see the file control. It's a folder, and the folder contains one single file, which basically is the one I showed you. Okay, now let's look at an actual system, a physical example. A physical example could be potentially, the simplest one is I can think of is a simple pendulum. Okay, so let's say that we have another example, and this is the example of a one link pendulum. And what we do here is we start the pendulum in this position. Theta equals 0 is the start. And there's some mass and some length. And then our goal is to get this to go in the upright position. Okay, and we want to go there from the 0 position to the upright position in the fastest possible time. Okay, so for a system like this, for any system which is a manipulator, a serial chain manipulator, the equations of motion are always of this form, which you can compute them using Euler-Lagrange equation. Now we do know what the equations of a pendulum like this. It's essentially, if this is mass and inertia, then it's I plus ml square. Here actually the mass is right here, I think. Q double dot plus, there is no Coriolis term. Okay, there could be damping at the pin joint, but there's no Coriolis term because you don't have more than one link, you don't really get it. And then the last part is mgl sine q, that's the nonlinear term, equals tau. So this is basically what we got from Euler-Lagrange. So we can investigate, and actually we'll investigate two controllers. One is if you did not know anything about, if you were doing this in the lab and you had no idea about control partitioning, then what I would do is I would just do a simple PD controller which goes like this. Torque equals minus Kp, the proportional gain, Q minus Q desired. So desired is 0. It's 5 divided by 2 minus Kd Q dot. Okay, that could be your first controller. And then the second controller, informed by what we know now about critical damping, we could have this controller, Kp Q minus Q desired minus Kd Q dot plus mgl sine q. So the example, this I have a code which will do this. It's 3A pendulum. So when you look at my Python files, you'll see this. And then the other one is 3B pendulum control partitioning. Okay, so we'll do it. First one, pretending we figured it out. We did the most reasonable thing to do, a proportional derivative control, see what happens, and then we'll take the partitioning one, which is ensured, which ensures that we get a critical damp system. Okay, so again, we're going to go from 0 to pi divided by 2. So this is pi divided by 2. This is pi divided by 2. And then here we also ensure that we choose kd as 2 square root kp. Right, this kd will be chosen like this to get critical damping. And here we have a tuning problem. Well, we have two numbers and we need to tune them so that we don't get, we get fastest response, that is go to 0 in the fastest amount of time. So first one is the naive PD controller, which does simple PD. And of course, as I said, that's be a tuning problem. So KP, KD are numbers I choose. Theta 1 ref is the final position. Here I just go with ODE int, I integrate from 0 to pi by 2. So this is my controller, exactly what I wrote. Here Q is theta. So we have theta 1 minus theta ref. And then equations and so on and so forth. I actually have, okay, I've written down as the ml squared divided by 4. It really doesn't matter as long as I have take care of it. So I assume that the mass is actually midway between the, uh, the pendulum. Okay, so initialize, simulate, and then see what happens. So it's 2 seconds. Okay. Okay, so that was fast, but here's how the response looks like. I start from 0 for the position, start for 0 for the velocity, and this is the torque. You can see that we want to go to pi divided by 2, which is 1.57 approximately. It shoots up and then damps out. Now, you could say that this is not satisfactory. If you see something like this, it means that the damping is not quite high. You could ramp up the damping. So I would, in this case, ramp up this damping to 20 maybe, and then see if it does better. I should have closed this. Okay, so that was fast too, but we can look at the response. So you can see it's getting better. The overshoot is there, but not so much. So it means that we're on the right track. We could maybe ramp it to 40 and then run this. And that seemed like it was good. So it's, you can see here it goes 0 and then about a little after between 0.25 and 0.5, about maybe 0.35 or something, it hits 0. Oh, well, it hits 1.57. Okay, so the question is, why tune it like this? Why not make it almost automatic? Well, here is the same system now using control partitioning. Okay, so I need more things here. I need the mass, inertia, and so on, because I would need it in the controller. I chose Kp to be 200, earlier it was 400, and 2 square root of Kp. Now, to be fair, I should just choose 400 here so that it's apples to apples. Kp is the free parameter, Kd depends on Kp, and then the reference is pi divided by 2. The only thing which is going to change between the two is this equation. Here we have, I fed m times Kp q minus q dot minus Kd times q dot, that's here. And then I have to supply it with estimate for the gravitational term. That's the control partitioning form. So let's run this. And remember, it was 0.35 approximate, or 0.3 or 0.35 to get to 0, to 1.57. So here, if you look at the response, it's maybe slightly, well, close to 0.25. Okay. So that's that. So it just shows you that you don't really need to do tuning when you have control partitioning working for you.